Hello everyone, welcome to another video in the series on electric vehicles conducted by Electronica Club, IIT Hyderabad. So in this video, we will be discussing about the common electrical machines that are used in the design of electric vehicles. Basically, an electrical machine just refers to a device or a machine that can convert either mechanical energy to electrical energy or electrical energy to mechanical energy. Now, the former, that is mechanical to electrical, is usually discussed in the context of power generation, inverters, generators, and so on. In the context of electric vehicles, we will be mainly discussing uh, how to convert electrical energy, that's the electrical power supply from the batteries, to the mechanical energy of the wheels, which would cause the motion of the vehicle. I mean, not necessarily wheels. If you're talking about automobiles or cars, this can also be talked in the context of um, flight, boat, submarine, whatever it is. Basically, essentially, we want to use electrical energy to move our vehicle, whatever it is. And for that movement, almost always there is something that has to rotate. In case of a car, it's wheels. In case of a boat or a submarine, it'll be propellers and so on. So without further much ado, let's dive into it. So yeah, first we'll just have a brief discussion of what an electric vehicle is. I'm sure, like in previous sessions and videos, you might have already been introduced to it a lot. Electric vehicles are just those that are partially or fully powered by electrical energy. The power is supplied by lithium ion batteries. Why do we use these specific batteries? Because they have great longevity and have excellent energy retention capabilities. Also, we can say that they are lightweight compared to other batteries like lead acid batteries, and they don't discharge as fast as nickel or dry cell batteries. So these are all the reasons why lithium ion batteries are preferred for the power supply. Electric vehicles are found to produce much lesser noise and vibrations compared to those that have diesel or gasoline run engines. And the obvious reason, the trivial reason I can think of is that those engines, this diesel, gasoline, all of they are collectively termed as internal combustion engines because they involve the combustion of fuels. So internal combustion IC engines have a lot of mechanical components like clutches, gears, flywheel, and pistons, and so on that, uh, as operation takes place, might give rise to unbalanced forces and unnecessary vibrations. This is not the case in electric vehicles where mechanical components are minimal. As a result, the vibrations are lesser. Two types of electric vehicles mainly: battery powered electric vehicles and plug in hybrid electric vehicles. So, BEVs solely use battery power, and as mentioned earlier, they have much fewer moving parts. There's no need of an exhaust, spark plugs, clutches, gears, etc. However, the main concern we have with them is their range. Long distance journeys, for long distance journeys and driving in hilly areas or rough terrain where large amount of torque or power is required, we the power of the electric vehicle drains very quickly, and we'll have to keep recharging it very frequently, which is not ideal because many places, especially India, electric vehicles are just being adopted, and it's not easy to find a charging station every 10 or 15 meters. So to overcome this problem, we have plug-in hybrid electric vehicles. As the name suggests, the power source is hybrid. It can either be battery power or power produced by burning fuels like petrol or diesel. As you can imagine, we will have to install an IC engine inside the vehicle, and this means noise, the issue of noise, vibration, manufacturing, maintenance costs, they all go up. But the good thing is that even if the battery power runs out, you still got the engine power to make up for it. So, how do these electric vehicles work? Basically, the power is provided by an electric motor, in contrast to IC engines, where the power is produced by burning a fuel, actuating a piston, and rotating a crankshaft. That's how an IC engine essentially works. So, electric vehicle is just directly a motor that produces the rotary motion. There are three main parts in an electric vehicle, components or units, if you may, in an electric vehicle. The first is an energy storage unit, the second is the controller unit, and the third is the propulsion system. The energy storage unit, as the name suggests, it stores power. Uh, Almost always we use a chemical battery. As mentioned earlier, lithium ion batteries are the most popular. Some cars also use fuel cells, but yeah, almost always we used chemical batteries, and the recharging can be done using either AC or DC power. Even household electricity would suffice. The controller unit is essentially the brain of the system. It decides how much energy from the energy storage unit has to be transmitted to the propulsion system. This is decided based on the driving conditions. When we are going up a slope or driving through a rough and unfamiliar terrain, the vehicle will need the propulsion systems would need more power, and that is determined by that will be detected by the controller, and accordingly it will allow more power to be transmitted to the propulsion systems. It also is responsible for converting AC to DC. So I mentioned earlier we can use AC also to recharge, even though the battery pack is essentially DC. Like it's batteries, it's DC batteries, it's not AC power. So we cannot directly recharge using AC. We need an AC to DC converter, and that is incorporated in the controller unit itself. Uh, the propulsion system mainly involves the electric motor that converts electrical energy to mechanical energy. This is the schematic of the electric vehicle and the various units. We'll be mainly focusing on the propulsion system, that is the electric motor. Now, how does an electric motor work? There are several kinds of electric motors with various nuances when it comes in terms of working, but mainly it depends on the interaction of the magnetic field with electric current. And any motor has two parts. One is the rotor. It is connected to the shaft, the crankshaft, which has to be rotated, and the stator. The stator does not rotate. Instead, the power is usually almost always the power is supplied to the stator. And how each motor differs is the way in which this power is converted to rotational kinetic energy of the rotor and the shaft. So yeah, this is how in the figure you can see essentially it's just two permanent magnets kept top and bottom to form the external magnetic field. Inside is a current carrying loop. We'll talk about this almost immediately. The different types of electric motors, they may or may not have a commutator. We'll come to what exactly a commutator is and how it works. Electric vehicles can have DC motor drives, induction motor drives, permanent magnetic brushless motor drive, a reluctance motor drive. It may have a regenerative braking system. This is essentially one where is incorporated in hybrid vehicles where the rotation of the engine is used to generate power which is stored in the battery pack. So it's like regeneration of power when the battery runs out, the IC engine will essentially recharge the battery pack. It's That's what basically regenerative braking means. and in-wheel motor technology. So we'll mainly be focusing on discussions on DC motors, induction motors, and brushless motors. And those are the most important things when it comes to the EV electrical machines in the EV industry. We'll first talk about DC motors. When I say DC motors, I mean brushed DC motors. In a basic DC motor, an armature, that is a coil, is placed in between the magnetic poles. An external DC source provides current to the armature winding, and that current will be flowing in it. Um, you can see that here. This is a current carrying coil, and as you can see, it's inside. It's within an external magnetic field, so it experiences a force called the Lorentz force, and the forces experienced by the coil are equal and opposite. They're on either end of the loop, and they cause the loop to rotate. So is that enough? Is that enough for a DC motor? No, that's the answer is no. Of course not. We don't want this to rotate. We want it to rotate continuously. We want it to give a continuous operation for a long time. And for that, we need to reverse the direction of current flow. Because otherwise what happens is, as you can see in the right schematic, the current carrying loop essentially acts as a magnet itself. And when the magnet aligns with the magnetic field, it won't move anymore. It will just stay there. And as I said, we want it to keep moving constantly. And for that, we need to do something, and that is reverse the polarity. So that reverse the polarity of this magnet, so that it will once again repel and try to um, arrange itself, and I mean, uh, station itself accordingly. And for that, what we use is a commutator. How does a commutator work? In this animation, we can see the commutator. It's a ring. It's a broken ring. It's in this case, it's broken into three pieces. This is the positive terminal. This is the negative terminal. And as you can see, this if we consider this segment, it first comes in contact with the negative terminal, then it comes around to the positive, then to the negative, then to the positive. When it comes to the positive, the current flows anti-clockwise, and when it goes to negative, it changes the direction towards clockwise. And that is essentially what happens in a commutator ring. It reverses the current in this manner. Uh, yeah, the brushes, we can't see the brushes here, but they are there. It's essentially what connects the commutator to the the coil. It's a conductor. It will be conducting. Yeah. So this is how a commutator and a brush together work to make sure a motor gives unidirectional and continuous rotation. And it goes without saying, if you reverse the current direction, the motor will be rotating in the opposite direction. If we want to, and we want to increase the speed of the motor, we have to vary the voltage that's applied to it. We'll now move to brushless motors. Now, how does a brushless motor pass the current to the rotor coils without any commutator brushes or anything like that? The answer is it doesn't, because there are no coils located on the rotor. The rotor is not a coil or an armature, it is a permanent magnet. The coils are located in the stator, and the stator does not rotate. Using variation of currents, we change around the magnetic field and make the permanent magnet align constantly with the magnetic field, instantaneous magnetic field, and hence make it rotate. And that's what mean when I say in the third point is vary by converting supplied DC power to a three-phase current. This video would hopefully make it clear to you all, guys.
In order to make the operation more reliable, more efficient, and less noisy, the recent trend has been to use
Sorry.
brushless DC motors. They are also lighter compared to brushed motors with the same power output. The brushes in conventional DC motors wear out over the time and may cause sparking. Thus, the brushed DC motor should never be used for operations that demand long life and reliability. Let's see how a brushless DC motor works. The rotor of a BLDC motor is a permanent magnet. The stator has a coil arrangement as shown. In order to make the operation more reliable, more stability, and become an electromagnet. By applying DC power to the coil will energize and become an electromagnet. The operation of a BLDC is based on the simple force interaction between the permanent magnet and the electromagnet. In this condition, when the coil A is energized, the opposite poles of the rotor and stator are attracted to each other. As the rotor nears coil A, coil B is energized. As the rotor nears coil B, coil C is energized. After that, coil A is energized with the opposite polarity. This process is repeated and the rotor continues to rotate. A humorous analogy to help remember it is to think of the
Okay. Yeah. So I hope that was a very good explanation. I hope it made everything clear. Essentially, just if we look go back to the video
in
again.
order to make the operation more
Sorry.
reliable, more effective is repeated and the rotor can
As you can see, it's a DC current. A constant voltage is provided, and it's turned into a three phase alternating current. The first phase we see one is high, the other two are low. The second phase, 1 and 3 are low, 2 is high. The third phase, 1 and 2 are low, 3 is high. And the same process continues in the next three phases, but in the opposite in the opposite sense. So using this, the and throughout all these phases, our rotor, that's a permanent magnet, will constantly try to keep aligning with the instantaneous magnetic field. When and this leads to a smooth rotation of the permanent magnet and hence the shaft itself. I hope it's clear.
in order to make the operation more
Moving on. Why are brushless motors superior compared to stepper motors, brushed motors, and many other kinds of motors? Brushless motors are becoming more and more popular nowadays. Why? Number one, efficiency. They can continuously operate by providing maximum rotational force or torque. This is not the case for a brushed motor. There, to deliver the same torque, it would have to use larger magnets. In other words, the a BLDC motor of a small size would deliver much more power than a brushed motor, which probably would be twice the size, would be bulky and not suitable for our application or requirement. Second advantage is controllability. Using feedback mechanisms, we can control the BLDC motor so that we can get the desired amount of torque and rotation speed. It is always to be remembered there's a trade off between these two parameters, torque and speed, because the product of torque and speed essentially gives you the power delivered by the motor. For a given power, according to what our requirement is, in case of an electric vehicle, it's the drive conditions, it's the terrain, and how much torque, more torque might be needed than speed in a hilly area or such a terrain. On the other hand, if we're cruising through a highway, we might need more speed than torque. So the good thing with a BLDC motor is that this control is very precise. We can get a torque that is very close to the desired torque, a speed that's very close to the desired speed. Very little deviation will be there. And this in turn reduces the energy consumption and the heat generation. As you can imagine, in other kind of motors, the deviation will be higher. It will produce more torque than is desired and hence will waste unnecessary energy and generate a bit of heat in the process as well. If it's powered by a battery, then it'll lengthen the battery life. VLDC motors are highly durable and they produce very little noise. And this is both due to the lack of brushes and commutators. In a brush motor, if you notice, the brush and the commutator are always in contact with the rotor. And that will produce sparks. Sparks that can be very dangerous. It can short circuit and cause a fire. Aside from that, it's a lot of wear and tear on these parts. Brushed motors cannot be used for those components that require a long life. They'll suffer wear and tear, frictional effects very quickly, and either they have to be repaired or most likely they will be replaced. Now, the application of brushless motors, due to their longevity, they are used in applications that require long operating life. Appliances like washing machines, air conditioners, in vacuum machines, hard disk drives. These these kind of things have to operate for years without any big trouble or technical issues, without having to replace the motor. And for that, a brushless motor is ideal. And due to their high efficiency, their high controllability, they've got very wide applications in robotics, service robots, and multi-rotor drones like quadcopters make use of brushless motors. So, moving on. This is a picture of a brushed DC motor. It's worn out. As you can see, the commutator. In the earlier example, we only saw three commutator segments, but here, as you can see, there are several, and one of them is very badly damaged because, as I said, a commutator is constantly in contact with the rotor, which will probably be rotating at a very high RPM, and over time, it's only natural that it'll undergo wear and tear. In this scenario, mostly you'll have to replace the motor itself. Now we'll move on from DC motors to AC motors. In AC motors, AC stands for alternating current. Basically, a current whose magnitude and direction constantly keeps changing. And the first kind of AC motor is the induction motor. It can either be single phase or three phase. Single phase motor leads to a pulsating magnetic field. Pulse just refers to high, low, high, low, high, 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 low. Such a rhythm will be known as a pulse. In a three-phase motor, we can get a rotating magnetic field. The we can it's essentially the output will be sinusoidal and continuous. Now, detailing on how an induction motor works. Basically, a current is there's a magnetic field surrounding this, and that magnet there's a constant changing magnetic flux surrounding this because of the rotating or pulsating magnetic field. This induces current or an EMF in the closed loop conductor of the rotor. And so obviously the rotor is not a permanent magnet here, it's a closed loop like the brushed DC motor we saw in the beginning. And when that induced current by Lenz's law, the rotor will always try to reduce the value of the current induced in it. And that current, since it is directly related to the relative speed between rotor and the rotation of the magnetic field. So to reduce the relative speed, it will try to match the speed of the magnetic field because relative speed is essentially the difference in the speeds. So it'll try to make this difference in the speed zero. How? By approaching the speed of the magnetic field. Because obviously you can't change the speed of the magnetic field itself. It only the rotor itself will try to rotate and match the speed. By nature, these motors are asynchronous. What does asynchronous mean? Base or no matter how much how what we see, the rotor will never have a speed equal to or greater than the magnetic field rotation speed. And the rotor can be of two types itself can be of two types: wound slip ring type or a squirrel cage type. The figures are shown here. It's to be noted that the stator in both of these cases is exactly the same, only the design of the rotor is different. Moving on now from asynchronous motors to synchronous motors. This is like the AC equivalent of a brushless DC motor. And as can be imagined, the difference is that the AC current is supplied instead of DC current. The synchronous word synchronous indicates the rotor spins at the same speed as the magnetic field in the windings. And because of this, it does not suffer any torque ripple. That basically means the torque delivered by this motor is continuous, and it also has high power density and starting torque. However, there is a disadvantage. Here, once again, the rotor, just like a BLDC, it's a permanent magnet. When we have a permanent magnet rotating, it leads to the formation of a back EMF. An EMF that essentially opposes the EMF or the supply voltage that is applied to the stator, and that could lead to problems such as formation of drag and heat that further ruins the magnetic properties of the rotor. That's not a good thing because the rotor is a permanent magnet. It's quite expensive. It's made of it has even some rare earth elements embedded in it. So for it to have undergo wear and tear, its replacement will not be easy at all. That's why we must try and tackle the problem of back EMF in a synchronous motor. Now, I mentioned a lot of motors and their workings. However, what application do they see in electric vehicles? Well, traditionally, in an electric vehicle for the propulsion system, we use AC motors. That is either the induction motor, or the synchronous motor. And a good example of this is the Tesla Model S. Why are they used? Because they have better traction. That is, they have a better grip on rough and uneven terrain. They, this operation is much smoother. They also generate more acceleration compared to their counterparts. However, recent times, companies like Chevrolet, Nissan, and even Tesla in its latest Model 3, they have moved on to permanent magnet BLDC motors. Why? Because there are significant size and weight advantages to it. It's also the cost compared to AC motors is much lesser. So you can imagine, like in a car, always in a vehicle, the optimization of size and weight are of utmost importance, and this is why BLDC motors are so useful. And because it was mentioned earlier, these motors can come in even the smallest of sizes and can still deliver the required power. If we are choosing an AC motor, we'll also have to choose whether we want a synchronous or an asynchronous one. And this depends on the customer's requirement. If the customer is a city driver, uh, they'll probably be stuck in traffic and all, and they'll have to stop the car, start it again. Acceleration and deceleration will happen very frequently. And for such a usage, synchronous motors are ideal. On the other hand, if the driver wants a high performance vehicle, one that can give either a good speed or a good torque and proper efficiency, then we can use induction or asynchronous motors. Brush motors have, as mentioned earlier, a very short lifespan and where they wear out very quickly. On the other hand, they cost very little. That's why they're used in windshield wipers and controlling windows. However, they're never used in any propulsion systems in any kind of vehicle because of the problems that we mentioned earlier. And there is also an inverter that converts the DC power supply from the battery pack to AC current, which might be required for the motors. And the reason I mention this because inverter also does come under an electrical machine, and yeah, that also is required. It's quite an important part in a EV. And yeah, that's it for presentation. Um, I hope you got an insight into uh, what electrical vehicles are and what kind of electrical machines are used in them. Uh, that's all. Thank you and have a great day. Thank you.